so this is it. But it's kind of, you can see, right? It's some number, right? So, and there's some comparisons, etc. Now, of course, we should, and my computer science colleagues want me to make this point as quickly as possible, so let's make it. This is still very small for cryptographic applications. So this would not be a fair comparison to things like Shor's algorithm, if you heard it. I mean, it's never going to factor anything large, but at least it's there in theory, right? And at least that's what it seems like. It's so difficult to get to 3 million logical qubits, etc. Anyway, but the point is, this is a very hard optimization problem that lets you, benchmark your hardware. That's it. Otherwise, factoring is just an example. Okay, don't get bogged, don't get distracted with factoring. It just shows you that there are very hard problems for which there may be no good solution other than probabilistically trying good states and doing this probabilistic gradient descent type thing. But the thing is, this is the random numbers that you needed in this exercise. Okay? And this is real data. We do it with digital circuits. It takes about 200 seconds. With MTJs, it could be less than it could be a few seconds, for example. That's the value proposition with things like magnetic tunnel junctions. Okay, so that sort of shows you that this idea. Now, I want to switch my last 10, 15 minutes. I want to show you how to build one. Right? Let's get to the magnetism, but this part was abstract. But how do you build a qubit with magnetism, right? And of course, so this is the building block that we want, right? So you want this tunable probability, right? And an obvious place to look at, or maybe not obvious, but a very fruitful exercise to think, is to think about a ferromagnet. Now, what is a ferromagnet? This is theoreticians' view of the magnet. You've been hearing wonderful talks from a lot of experts, etc. So I hope this isn't too simple for you, but we have a red state and a blue state, and they're separated by some energy barrier, 40 kT or something like that, right? And then people will tell you, okay, my fridge magnet that I kind of pinned to my fridge, that stays there for 10 years. How do you understand that? And people will say, yeah, that 10 years, the time is some exponential of that energy barrier. Right? That's how, and there's a constant, obviously. There's a lot of physics in this constant. You can talk to Professor Fukami, for example. Right? But usually, I think you would agree that number is somewhere around picoseconds to nanoseconds. For this discussion, it doesn't matter. What matters is you can go to Mathematica now and calculate exponential 4D and multiply it with picoseconds or nanoseconds. You're going to get some number of years. That's why in MRAM and things like that, people will say that this has to be 40 to 60. Okay? That's the retention. But if you believe in that formula, that's the weird thing with exponentials. If you make that energy barrier kT or so, then you're predicting this fluctuation in a matter of picoseconds to nanoseconds, right? That's if you believe in that formula. Now, those of you who are experts in magnetism are already troubled, because if I reduce this barrier too much, I won't be able to distinguish red and blue. I'll be all over the place, actually. So this toy model breaks down very quickly. But nonetheless, we've done this theory of, many years ago now, and I'll tell you a story about this. But if you have an MTJ that I'm not going to explain to this crowd, and you replace it with an unstable magnet like this, something like you expect something like this. As a function of time, you expect fluctuations, right? And this is kind of, you see, this is a sub-kT magnet, so you're kind of seeing that it's kind of continuous rather than telegraphic, right? So when we did the theory, I remember being told by experts of our community and being warned that at that time this wasn't experimental. Okay, and we were seeing it numerically, and then we had a good analytical theory, and then others did actually follow-up studies, etc. And people used to say, random walks are slow. You're out of your mind. You're never going to see this picosecond to nanosecond fluctuation. Okay, never going to happen, right? And of course, at that point, you ask yourself, how could I be? How could there be no theory on something so simple, a single magnetic body and low barrier limit? And here's so Professor Fukami yesterday showed, plus he went way back, right? 200 years of magnetism research. How can you have something new about something so simple? And the answer is this. This is a very famous paper by Brown, which is kind of a hero of this community, and if you don't know him, look him up, right? This is William Fuller Brown. He was at, this paper seems to be written in Israel, but he was actually at the University of Minnesota. And this is kind of an important paper. It's got a lot of citations. It has this Fokker-Planck equations that you guys may be using. That's kind of a general theory, that connects to LLG in a probabilistic sense, etc., right? So he derives that equation here, right? And even today, this is a very useful thing to think about. And if you go to that paper, you see low barrier energy approximation. Great. So let me read what the great Brown had to say about this. And formulas on perturbation theory. And then he says, and then this is how he concludes. He says, unfortunately, these formulas apply to the case of least interest, in which the anisotropy is small, which is this low barrier limit. So this is a little bit like that anti-ferromagnetism comment from Neil, right? That it's never going to be useful. So Brown clearly can do the math, but he doesn't want to, because it's, who wants a stochastic fluctuating magnet, right? So this was of course 60 years ago now, right? So that's the reason we could have some new theory, because people could do it, but they didn't care, right? But the randomness seems like a very important, interesting application of these magnets. Okay, so that's usually what the experts would tell you in those days. And just to complete that story, after the theory, again. People, experts who could do these experiments, the Tohoku lab, Ono and Fukami, and then Jonathan Sun, and then others now, they have shown these nanosecond fluctuations with MTJs. So that was very exciting. Okay, so you could actually have nanosecond fluctuations, and you see, this is the most amazing thing to see in the lab. You have this resistance that goes 10K, 20K, 10K, 20K randomly in nanoseconds, and you can see it in the lab, and that's a very complicated function, and that comes for free, literally. So and you can have millions of them if you want. And remember that optimization example I showed you, 123 trillion random numbers. Now you can get, if you're getting a billion a second, right? Then you can have a million of them, and you get that. That's nothing, right? You can have both scale and time, right? So that's kind of exciting. Okay, so there's a lot of, and we do these, so we make those, so I still haven't shown you how to build the pivot. Maybe I first show you that, but then I digress here, so let me just go here first. So how do you make the pivot? Because this is just magnetism that's fluctuating. To do a pivot, what you do is you use the magnet, but then we want, we're electrical engineers, we want to have this electrically. The magnetism is, it's great, magnetism to study is wonderful, but if you want to do something with it, it needs to be electrical in and electrical out. And the way we do it is we have an MTJ, and you attach an inverter to it. So this circuit you could show produces approximately what you want from that tunable randomness. Okay, and it's kind of a simple voltage divider. I can explain that to you, but you can probably work it out. It's this input voltage to the transistor changes the resistance of the transistor. It's either on or off, right? And so if it's off, then you're here. If it's on, then you're here. And when it matches the MTJ resistance, you have a lot of fluctuation here that's being amplified by the inverter. That's it. This is kind of simple. Okay? There's nothing complicated about this. Now, at this point, there's a very common thing that I get, and I think as a magnetism crowd, as scientists, this is something that I should tell you. There's very often this question of, all you need seems to be randomness. Why do I care about the MTJ? All you have is a random number generator. Now, yes and no. Now, the problem with, so I'll show you now something that's for freshman physics, right? So suppose you have an RC circuit. Right? So this is a common question I get all the time. And in normal talks, I don't have the time or the luxury to get into this field that the summer school gives me an opportunity. Right? So suppose one thing you learn in freshman physics is that every resistor has a noise. Right? And what's the name for that? Does anyone know? What do we call the resistor noise in addition to thermal noise? We say, does anyone know? We say white noise, but Johnson-Nyquist, right? That's, if you go to Wikipedia, then they'll say they'll have a theory of this, and I can never understand that page. You can never understand physics from Wikipedia anyway. But that's an example of that. You go to that page and you're like, who wrote this? What is this? So I'll give you something for this circuit that you'll never forget, and I think it's really simple. Right? And it goes back to that Boltzmann law. So you write an energy function. Right? There is an energy that you can write here. And CV squared over 2 is something you all know. And then QV, you know, has the units of energy. Right? If I have a battery here, then I should put, and this you have to believe me for the moment, that the energy for that system should be half CV squared minus QV in. That minus sign is very important. Okay? Now, this is the sort of the energy as a function of that voltage on that capacitor. Okay? Now that's the energy. So how do you proceed here? You solve the Boltzmann law, right? You say in equilibrium, in equilibrium, this has to follow the famous important Boltzmann law. Right? And that was, remember, that was in the p bits in a very different context. Now this is in physics. Right? And what do you say? Okay, I've got a normalization constant. It's a probability distribution. You have to be somewhere. Right? So here's a normalization constant 1 over z, exponential minus energy over kT. Okay, that's the only thing you need to remember. This is something you already know. You write down the energy. Go do this for the inductor. You can. Okay? So CV squared minus QV. So how do I proceed? How do I find the probability distribution? The Z is annoying, right? I mean, I could put the VCs and Cs and everything to this energy, but I don't know the Z. How do I find the Z? I mean, this is a probability, so it has to add up to 1. So you integrate this from minus infinity to infinity, and then you say you have to be somewhere. You have to choose a potential, right? So that's how you do this. And you can go to Mathematica or just take a picture of this and give it to GPT, and then it'll write the mathematical code for you, and then this is the answer. And this answer is something you may recognize. This is a Gaussian, as one might expect. So, one of you, one of your colleagues was expecting Gaussian noise. You don't have to assume that. Okay, you can just write down the energy, assume the Boltzmann law, and out comes a Gaussian. So if you just plot that now, but for different V in, this is what you see. Okay, so a student did this for me, and they were very excited to get the same behavior from SPICE. HSPICE, the numerical circuit simulator. To me, the fact that SPICE matched this is testament to SPICE working, because Boltzmann law can obviously not be incorrect, right? So SPICE gets the noise correctly. So this is a histogram of the voltages, okay, as a function of the probability distribution. And what does this figure tell you? This tells you that your maximum chance, let's look at the 0 case. This says at equilibrium, you should be, if the V in is 0, you should most likely be 0. Well, duh. I mean, like if this is 0, obviously everybody would put 0 on the capacitor. But it tells you something more. All that work, and you're rewarded with something. It tells you, no, but there's going to be noise actually. Actually, you're going to be a Gaussian. You won't see a 0. Your mean will be 0, but you'll fluctuate. Interesting. So how much will I fluctuate? Well, that's the standard deviation of this Gaussian, and it's right here. Right? It's kT over C square root is the fluctuation. But before I get to kT over C, if you push this with let's say that you have a V in of 10 microvolts, what would you expect at steady state on the capacitor? 10 microvolts. Right? It'll just charge up. Right? And the math seems to catch that. If you put V in is equal to 10 microvolts in that equation, then the mean is, you're basically deriving the CV in has to be VC, right? That seems to be coming out of the math, right? In equilibrium, you have to be 10 microvolts, okay? Very good. But then that spread, so let's calculate that spread. So it looks like the RMS, or the squared mean fluctuation on that resistance or capacitance is going to be kT over C square root. That's a beautiful result, and that's something you could probably, you could study the equipartition, things like that. You could probably get to this result in a less rigorous way. But I find this to be, other than integrals that you don't have to take, I find this to be very instructive. This is a better way to write that wiki page. It's not written like this. You'll see this, but it'll come from some complicated thing, okay? So that's V squared. So let's do some math here. KT is, at room temperature, you can't change it. 26 or 25.8 millielectron volts, right? Now, 100 attofarads. Can anybody tell me what is this, the order of magnitude of this capacitance? This is something that you should know. Like, is it a big capacitance, small capacitance? What do you guys think? Atto is 10 to the power 18, so it's kind of a small capacitance. But this is about the gate capacitance of your transistor. Minimum width transistor would be around of the order of something like, I mean, it's obviously a function of voltage and whatnot, but it changes between 100 and 400 attofarads. And it's mighty small. It's really small. Okay, in fact, it's incredible. I'm not sure if, it's easy to measure such capacitances. But you see, if you want that fluctuation to be large, remember, why are we here? We're discussing all this because we want a noise source, and resistor is a very obvious noise source. And it seems to be that even if you have such a small capacitance, your fluctuations are 5 millivolts. It's not a lot, actually. And if you increase this capacitance, that number goes down. I deliberately chose something that is, in fact, unrealistically small to show you that you don't get free fluctuations at the output of a capacitor or a resistor for free. So what the MTJ is doing is kind of remarkable. Now let's switch to the MTJ physics. Okay, this is basic freshman physics.
What if you take that voltage as the amplifier?
Right. So Professor Prem has a very good point. You can take this voltage. Now, if you give it to an inverter, it won't be able to see this. This is too small for an inverter. So you need a really sort of a serious card-carrying amplifier to amplify this. And that's a lot of transistors, and that's a lot of power. And people have tried this. People were trying probabilistic computing, and then you have an amplifier per p-bit, and then you want 1,000,000 amplifiers for 1,000,000, and that didn't work. Okay, so, but you could do that, and people tried that. You could amplify it, but it becomes too expensive because everybody needs it. Everybody needs their private amplifier. Now let's study the MTJ physics. 5 millivolts is the number to remember. Well, 5 millivolts, don't remember 5 millivolts. Remember KT over C. So actually don't remember KT over C. Just remember the Boltzmann law and the capacitor energy, and then you can find yourself here. Then anybody can plug the numbers in. Okay, but 5 millivolts for the next 5 seconds. So the MTJ, I talked about a voltage divider, right? So I talked about a voltage divider. So suppose my MTJ fluctuates, let's say every whatever picosecond. That doesn't matter now, okay? But what matters is I go from 10K to 20K. These numbers are, if you talk to Professor Fukami, these numbers are real. This is not a huge hero TMR or anything. This is what Professor Fukami can probably improve or beat this, right? He was showing TMR data, right? This is a TMR of maybe 200% or less, actually, 150 or whatever. Okay, now this is a voltage divider. All of you know how to calculate this via output. That would be, it looks like I calculated it incorrectly. It looks like, shouldn't it be Rn-MOS over Rn-MOS over Rn-3? I think so. But forgive me for that. I think this divider equation is wrong. But the basic math is, this fluctuation now, the V0, remember KT is KT. I still have access to 25 millielectron volts. But if my MTJ is going from 10K to 20K, and if the transistor is at 10K, for a drop of a volt, I'm getting 150 millivolts of fluctuations. That's roughly, that's of the order of 2 orders compared to what we had with that hero capacitance. Okay? No amplifier needed. This can and does easily drive the next p-bit because it's enough. Okay, so this is very large. So it seems like this, and I'd like you to appreciate what's happening here. You've got KT, watch out, KT energy is 25 millielectron volts. That somehow became 150 millivolts. And for an electron, it's 150. So actually, MTJ is a noise amplifier. Okay, and the collective physics of exchange, TMR, magnetism, transport, all of that is coming together in a very nice, beautiful way here. So my answer usually, it took a long time here, but my answer usually about, if somebody asks me what's special about the MTJ is this. So you probably need something like this if you want to use noise as a resource, because there seems to be some collective action going on here. Okay? So it looks like I'm running out of time. So I have about 3 or 4 minutes. I obviously have more, but I think these are the important points to mention, and maybe I could just show you. So this is kind of research level. Now we can be a little bit informal, right? So these are computers or p-bit computers that we've built over the years. So we started with 8 p-bits. It's exactly the same architecture that I showed you, that recurrent feedback. So there was MTJs, that this was done by Professor Fukami's wonderful graduate student at that time. Now he's at NIST. And he had these 8 MTJs, and he solved some optimization problem, he factored some number. But what I want to tell you is, in the last few years, around 2020, I changed jobs, and this experiment was so hard, and I wanted to do harder and bigger things, okay? Because I was impatient, and I didn't want to do this, with MTJs. It took us a few years just to get to this 8-qubit computer. And then the obvious question that somebody could ask is, yeah, but why don't you make use of digital computers? And this is, for those of you who don't know, this is a field programmable gate array. And I recommend everyone to learn just a little bit. And if, you don't even need to learn a new language. You can just, ask the AI. But the thing is, this has 100 billion transistors or so, that chip here. And we could only fit 5,000 qubits in it. And that should tell you that's because every qubit is very expensive. Right? Because, we came from magnetism, but we thought, okay, let's use digital logic to our advantage. So we could do bigger things, okay? So we could factor much bigger numbers. We learned a lot about the architecture and details. But it's actually my respect to the MTJ and magnetism after going through this digital CMOS exercise increased tremendously. Because I realized that even if I use 100 billion transistors, these are the numbers that we're always going to be stuck at. Right? But with MTJs, maybe you can go much bigger. Right? And recently I've been connecting MTJs with FPGAs, and maybe the random number could come from the outside world, and so on and so forth. You can go read these papers. But I'd like to make one more point. I'm done in maybe 3 minutes. Okay? So this is the point that I'd like to make to you. So this is something that we've gone over extensively. This is the MTJ-based qubit. This is the digital qubit, okay? So in digital CMOS, you can make a qubit. You need a random number generator. Okay, so I apologize for the acronyms here. This is pseudo-random number generator. This is linear feedback shift register. It's the cheapest random number generator money can buy in CMOS. Okay, and this is not a Japanese word. This is XOR shift rotate. Okay, this is Doshira. Okay, this is a slightly more expensive random number generator. So I just want you to see this final thing, and then we're done. Okay, so the LFSR, the cheapest random number money can buy, at some small bit range, 32 bits, it costs 1,000 transistors a piece. Okay, you want tunability. Okay, tunability isn't free. 5,000 transistors. I'm talking 1 qubit. Okay, but then you realize this is such a low quality, such a bad random number generator. It breaks down for anything more complicated than simple optimization problems. So now you have to pay for Zoshiro. Well, now for just the PRNG hikes up to 7,500 transistors. Tunability adds another 4,000, just like previously. Now you're looking at, and these numbers are integers. So we've synthesized them. You're looking at 11,546 transistors per qubit. Whereas this guy that you had here was a few transistors and an MTJ. Okay, it's kind of drastic. So if you want a 10 million qubit computer, which is something we obviously want, where AI is going and whatnot, that's just 100 billion transistors for the qubit. Okay, so that's not happening. So now you can see why we're stuck at 5,000 qubits, even with the world's best digital technology. Okay? So that's what this MTJ-based qubit can give us. Maybe, and this is not even 1 megabyte. 10 million is 125 megabytes, right? And people have put 1 gigabyte, gigabit, whatever MTJs in these MRAM chips, right? So there's a lot to be done. Okay, so I'd like to wrap up and just kind of skip to the end, and I'll leave you with a model of the field that I'm working on, and I hope this stimulates you and you get into this. And so this is something that I didn't invent this, but people have been trying to build computers with the idea of letting physics doing the computing. Okay, so let physics do the computing is the idea that you build something like a system that looks like a physical system that evolves on its own, and it solves a problem for you. And you could put quantum computing in this category. And qubit computing is also a little bit similar. And so the key aspects we've emphasized, asynchronousness was important. no two MTJ fires at the same time, so there's no problem with clocks. Right? And in physics, one thing you learn is things are usually local. If there's a fire in this room, it's going to take some time for it. If there's a fire in this box, let's say something happened on the top left, it's going to take some time to reach the other end. It doesn't mean it's not connected. It just isn't all-to-all connected. Okay? And in machine learning, people have some trouble understanding. They got spoiled with their fully connected models. Okay? But in physics and your chips, your brain, nothing is fully connected. Okay, so I think I could stop there, and I hope I was able to give you a flavor. So thank you very much, and enjoy the rest. Okay, thanks.
Let's take one or two questions from the audience.
Yeah, it's a very interesting field. So I was wondering how. So it's important to get this very, very small energy barrier for your ferromagnet. So is this a particular engineering challenge to do this? Because you want to have a soft material but also very clearly define its states.
Yeah, I mean, I think there has been a lot of ideas, and beyond ideas, a lot of experimental demonstrations now. If you're a PMA, what they do is, first of all, you don't have to be 0, 0. You can be close to 0 and it'll still work. It's still fine. And circular magnets are my favorite. So it's almost like you have no anisotropy in the plane, but you can't go out of the plane. And you, like a random clock, you're kind of pointing. And I don't know if they have built this, but this is the type of thing that, but many other in-plane configurations, PMA. So there's been so many different flavors. So we should discuss details probably. But one thing I'll say is, this barrier doesn't need to be, or probably can never be, absolutely 0.
Yes.
But you know, you learn exponential x over kt, if x is small, is 1 plus x, right? I mean, it's not an exponential anymore. So that's okay, so
Anyway, yeah, thank you.
okay, thank you. Yeah.
I'm curious about the operation of the MTJ.
Yes.
So you say the thermal stability factor is very small, so that the magnetization direction will change with time, and then I'm thinking if the right current is needed, or just change with time so we can dictate it.
No, but in this thing, there is no right current, or
Yes.
there is no right, because all you want is you want the world's worst memory device. You want it to kind of flip states all the time and be insensitive to right currents. You just want a random number that's unaffected. So it's kind of the entire MTJ thinking is changed, and there's ways of making it very hard against right currents, which is exactly the opposite of what you want in an STT-MRAM situation. But you want it to be magnetically soft. And remarkably, the nonlinear nature of magnetism, in-plane magnets, especially with, let's say, double free layers and so on, are very hard to write, but they're magnetically very soft. These are real experiments.
But the critical thing is the redisturbed, right? So the recurrent will maybe become the right current for this.
Right. Well, if you kill the spin torque, which you can in these double free structure, for example, no fixed layers, 2 free magnets that are fluctuating. Nobody can win over the other one, but you can still read the state by just pushing a little bit of current, because TMR still exists. Right? So,
but the other idea is to use a very nice MTJ with high thermal stability. You just need to set the right current to be 50%.
Right, that would be like flipping a coin, but the problem, I feel, and people are, just to be clear, people are proposing p-bits like that, but one problem with that is you probably have to reset. And that kind of, we want something that's kind of going all the time as a physical system. But in the example you've given, if I have 1,000,000 p-bits, I have to flip one, reset, flip the other, reset. It's not massively parallel anymore. But people are interested in your idea as well, so it exists, don't get me wrong.
Thank you.
Okay, thank you.
So, when you're solving the inverse problem and you fix the answer, basically, do the solutions also fluctuate at the same time scale?
Yeah, that's a very good point. We do what's called a simulated annealing. You know, in experiments, people anneal their materials, right? So you start from a high temperature, algorithmic temperature. So the conductance example in the simplest p-bit circuit I showed. So we start from a low conductance and we increase it over time. So by the time you find a good answer, you don't want to lose it because p-bit is just going all over the place. Right? So that's a good point that I did not mention at all. But those are the types of things you would have to do.
So you have explained the right side of the efficiencies. What are the challenges?
A lot of challenges, right? So, and I stand for digital CMOS as well. In my lab, half my group is doing digital CMOS, and digital CMOS people are always very tough on MTJ people because they can do thousands of p-bits. Whereas the largest P circuit that I know is actually Professor Yunsu, has 80 MTJs, but that's a very small number. So unless we can integrate this and put a lot of effort in the engineering of low barrier magnets, right, in MTJ design, controlling variations, make them fast, get rid of DACs, and have a big working system, only then this might have a chance of actually surviving the valley of death. Right now, it still is a laboratory experiment. That said, with FPGAs, we could solve some, maybe, because to me, over time, it became more than the MTJ. It became an abstraction, and it's connected to powerful algorithms like simulated annealing, optimization. So you could do it with CMOS. But for a true breakthrough, we need a lot of work in making it scalable, and it's still kind of at the lab level as far as the MTJ is concerned. I hope that gives you an accurate, fair idea of where things are. Okay, maybe that's a good place to stop, or more questions?
So, if no more questions, so thanks Kerem again. So based on